All right, so next up we're going to talk about logarithmic functions. So as a reminder from last year, what are logarithms? Logarithms are used to solve for unknown exponents. So for instance, if I had an example like example 1, 2 to the y power equals 8, and I want to solve for y. You could probably come up with this without having to use logarithms. Some of them are easy enough to do that. If you remember, 2 to the third power would equal 8. One of the things we also learned last year was if we could rewrite things as powers of the same base. For instance, I could rewrite 8 as being 2 to the third power. 2 times 2 times 2 is 8. If I can get these bases to match, the only way they'd be equal is if our exponents also matched or were also equal. So from that, I can conclude y has to equal 3. 2 to the third power is 8. We didn't really need to use a logarithm to answer that question. However, example 2, 5 to some power being equal to 8 is much more complicated to answer. I could roughly estimate it by knowing 5 to the first power is 5 and 5 to the second power is 25. And 8 is between these values, obviously much closer to 5. So, I might guess it's somewhere near 1.1, 1.2-ish. As a guess, I wouldn't go much further than 1.2 towards 2 because it's way closer to 5 than it is 25. But to answer this, we would need to use a logarithm. Okay, so one of the things that it's going to be really helpful to do is be able to switch from exponential form to log form. And that will help you if you ever forget some of these properties we're going to learn. You can always rederive them by going from one form to the other. Okay, so this statement, if I have something in exponential form, b to the y power equals x, we can write that as a logarithm as well. Okay, we can go from one form to the other. And these are basically saying the same thing, but in different ways. This is exponential form of this equation, and this is the log form of this equation. So one way to remember how to go from one to the other. The base of my exponent, okay, in this case b, is the base of my logarithm. So that's our tip down here. The base of the exponent is the base of the logarithm, and vice versa. So that's why I like the letter b there. Easy to remember, base. Okay. Remember that we use logarithms to solve for the unknown exponent. So my logarithm is always equal to the exponent. So it's always equal to y. And that helps me remember what we're taking the logarithm of is x. So if I were to box that in here, that's what we're taking the logarithm of. And if you remember the base when we write logarithms, that's written as a subscript. It's like an exponent, but instead of being up top, it's down below. And there are some restrictions on this. We'll talk about them later when we talk about graphing. Okay, so the base of the exponent is the base of the logarithm, and the logarithm always equals the exponent. That'll help us switch between one and the other. Okay, so next let's take a look at some examples here. Okay, so one of the things we're going to do, like I said, is switch from one form to the other. So practice changing from log to exponential and vice versa. Hint, all the following are true statements. So obviously 7 squared is equal to 49. That's an exponential form. And to write this in log form, remember that the base of my logarithm, well, that's not very dark. Let's change this. The base of my logarithm is the same as the base of my exponent. So log base 7. And I always like to set up of something equals something. Remember, what does my logarithm always equal? The exponent. So that's what goes out here. And that reminds me that we're taking the log of 49. Log base 7 of 49 equals 2. And you can plug that in your calculator to confirm that. So let's do the same thing. Writing this in log form. 36, by the way, to the 1/2 power. If you remember, to the 1/2 power means the same thing as the second root or square root of 36, which is 6. So again, another true statement here. So if we're writing this in log form though, the base of my logarithm is the base of my exponent. So log base 36 of something equals something. And in this case, remember that it always equals our exponent. And what we're taking the logarithm of is our 6. And you can check that in your calculator. If you put in log base 36 of 6, And I'll do that very quickly. Here's the log key. I have to hit Control. Log base, whoops, I'm in the graph. I don't want the graph that. Sorry, log base 36 of 6 should give me 1/2 or 0.5. And yep, we've confirmed our answer there. Okay, so let's go backwards. Writing it from log form and exponential form. So here's the base of my exponent, 3 to some power. Remember that my logarithm equals the exponent, so in this case 2 is equal to 9. 3 squared equals 9, nice true statement. Okay, similarly here, 5 is the base of my exponent. 3 is my exponent. And that equals what we're taking the log of, the 125. And yep, 5 times 5 times 5 is 125. Switching it up again, let's go back to log form from exponential form. So here's the base of my logarithm. Log base 2/3 of something equals something. Remember that my exponent is what my log equals. So it equals 2. And what we're taking the log of is 4/9. So you could try that in the calculator too. If you put in log of 2/3 and 4/9 on the inside, there it is. It's exactly equal to 2. So another true statement. Okay, let's do one more. 25, the base of my logarithm is the base of my exponent, to the 1/2 power, or my logarithm equals the exponent, is equal to 5. And again, remember, to the 1/2 power means like the square root. So square root of 25 is 5. Okay, so now we've practiced going from one to the other. Let's talk about other ways you can read logarithms. First of all, anytime we're asked to find the value of or evaluate a logarithm, always set it equal to some value. So in this case, say x. And if you change it to exponential form, we can do what we talked about in the first part of the notes. So let's write it in exponential form. 3 to the x power equals 81. And this can be evaluated without a calculator. Again, I could just type in log base 3 of 81. It will give me the answer in a calculator. But to do it by hand, we can rewrite these as powers of the same base. I can rewrite 81 as either 9 squared, although that wouldn't match my 3, or 3 to the 4th power. So if you did like a factor tree of 81, you'd find out that you'd get 9 and 9 from each of those pairs of 9s. You get a couple 3s. So we end up with 3 to the 4th. And now that my bases match, I know that x will have to equal 4. And so this logarithm is equal to 4. Another way to try to answer these or solve them is to know kind of what the logarithm's asking. And it's saying 3 to what power is 81? And sometimes they'll have nice whole number answers. In this case, 3 to the 4th power. So that's what the value of that logarithm is. Okay, let's try some of these other ones. They're a little more complicated. So again, one of the things I can do here, if they give you a decimal, we're going to turn it into the fraction. And to turn any decimal into a fraction, most of you guys will know 0.25 is 1/4. But if it was more complicated than that, we're going to start by just making a fraction with its place value, 25 100ths. And of course, if you reduce that fraction, that becomes 1/4. It's log base 2 of 1/4 equals x. And anytime I have a number in the denominator, to get it out of there, we're going to go back and use negative exponents. So I could write this as 4 to the negative 1st power. And really at any point from here or here, we could go to that exponential form. So let's do that. 2 to the x power equals 4 to the negative 1st. Well, I can rewrite these as powers of the same base. 4 can be rewritten as 2 squared. And anytime I kind of rewrite something as a power as the same base, I need to multiply it by any existing exponent. So 2 times negative 1 is negative 2. And now that my bases match, I know that x equals negative 2. So I could check that in my calculator. Log base 2 of 0.25. So I'll use the log key again. Log base 2 of 0.25 is -2. Feels good. All right, let's try another one here. Holy moly. All right, our next one. We're going to say equals x. And again, we're going to go to exponential form. I want to know 8 to what power is 2? Well, I know 8 to the first power is 8, so it's got to be less than 8. Or, sorry, less than 1. But if you go to exponential form, 8 to the x power equals 2. I can actually this time rewrite the 8 as a power of 2. That's 2 cubed times the x that was already there. I almost forgot about it. Is equal to 2 to the first. And there's always that hidden 1 when you just have a number without an exponent written. And now that my bases are already match, I can say 3x has to equal 1. And dividing by 3, I get that x is 1/3. 8 to the 1/3 power. Remember, that means the third root or cube root of 8 is 2. And that sounds correct to me. The cube root of 8 is 2. Okay, last one here. 3 to the x power is equal to 1/9. We're just going to exponential form again. To get this 9 out of there, we're going to use a negative exponent. So 9 to the negative first. And of course, 9 can be rewritten as a power of 3. It's 3 squared times that -1. And now that my bases match, I know that x has to equal -2. And there we go. 3 to the -2nd power is 1/9. Okay, so as a reminder, some buttons on our calculator, that the log key defaults to log base 10. And so a lot of calculators that don't let you put in other bases only do log base 10. And sometimes you have to use that change of base formula to do other ones. We'll go over that, I think, next class. The other one is, and that's called the common log because it's used so often. If you have log base e, that's called the natural log. And that's ln on our calculators. That's also used very, very often. Okay, let's take a look at some more properties and then some examples. So these are derived from the definition of a logarithm. And to understand why these are true, log of any base of 1 will always equal 0. To figure out why, let's put it in exponential form. b, which could be any base, to the 0 power. Oh, well, what's anything to the 0 power always equal by properties of exponents? 1. So no matter what my base is, if I take the log of 1, it will always equal 0 for this reason. So sometimes you'll see that. That's kind of a tricky one because you don't see it very often. But if you go to this form, you might remember it. Okay, so let's look at our next one. Log base b of b equals 1. So if we write this in exponential form, b to the first power equals b. And that seems to make sense to me. But what this really tells me is if the base and what we're taking the logarithm of match. Like say if you look down here at example C, log base 5 of 5 will always equal 1 because 5 to the first power equals 5. So here our answer is just 1. And if you forgot it, you could rederive it by just putting this in exponential form. You'd say 5 to the x, to the x power is equal to 5 to the first. Well, you'd probably just write 5 and then remember there's a 1 there, and now x does have to equal 1. There's your answer for example C. Let's look at our next one. It's kind of an extension of 2, and it's going to end up equaling this exponent for basically the same reason. So let's take a look at that. b to the x power equals b to the x power, and that makes sense. So with the base and what I'm taking the logarithm of match again, but this time there's an exponent on the inside. That exponent is what it evaluates. So you can imagine the exponent up here being 1, and that's why this is 1. But if this was like log base 5 of 5 to the third power, my answer ends up being 3. Okay, pretty kind of the same reason here. Again, and if you forgot these properties, if you write it in this form, it'll make sense again. Our last one is actually in exponential form, and it will make more sense why this is true if we write it as a log. But basically, if the base of my exponent is down here, and we raise it to the log of the same base of whatever we're taking the logarithm of, in this case x, our answer ends up being that x. So let's take a look. It's in exponential form. We're going to write it as a logarithm. Log base b, that's the base of my exponent, of something equals something. That's a b, by the way. Remember that my logarithm always equals the exponent, which happens to be log base b of x. And for these things to be equal, this value has to also be x. So b to the x power equals log base b of x. And if you rewrite this, you can see that they do match, they are equal. So a good example of this, we'll skip down to number 4 for a second. If I have 4 to the log base 4 of 3 power, my answer ends up just being 3. Okay. We can look at that kind of why if we look at this example back here. A is a couple ways to solve this. Traditionally, the way I taught last year, if you had my class last year, was if we can get logarithms, a single logarithm on each side equal to each other, and they have the same base, log base 5 to log base 5, the only way these values would ever be equal is if the inside values were also equal. So here x would have to equal 8. And that's our solution. Now another way of solving these is what's called exponentiating each side. And what we're doing is we're actually going to take this expression and make it an exponent on each side. And what we're going to write as the base of our exponent is the same base of our logarithm. We're actually using this property in 4. So because my base is 5, we'd actually write it like this. 5 to the log base 5 of x equals 5 to the log base 5 of 8. And via this property, this side becomes x. And then via this property again, this side becomes 8, and we can get to our answer that way. Most people, when they see this, they would write it like this. They'd actually just write a big 5 and then make those look like exponents because now they're small and up to the right. And so this side evaluates to x, this side evaluates to 8. You technically get to the same place. I don't know, for me as a student, this way was really confusing. Just knowing that if I can get these logs equal, the insides have to be equal, that made so much more sense to me when I learned this as a teacher. So, you'll probably see this in the future. I still think it's confusing. Whichever way you want to do it, up to you. All right, let's go to our next one. 5 to what power would equal 1? So if you look back up in our properties, remember that any base to the 0 power. And if I write this in exponential form, 5 to the x equals 1. I could rewrite this 1 as being 5 to the 0. It's a very smart way to try to rederive that property, and therefore x has to equal 0. I could make these bases match and write that to the 0 because anything to the 0 power is equivalent to 1. But our answer here for b is that x equals 0. Okay? All right, tons of notes today. I'm sorry, you might have to go back and pause or ask the sub pause to get some of these. So next we're going to talk about graphs of the log functions. Log functions are the inverse of exponential functions. So to save time, I'm not going to rederive the whole thing, but if you took the exponential functions we did the other day, you swapped x and y, and tried to get y by itself, well, if I wrote this in log form, it'd be log base b of x equals y, equals my exponent. And that's our log function. So we swapped x and y, solved for y, therefore it is the inverse of an exponential function. Okay, so this actually has the same stipulations that we had on the exponential function. My base cannot be 0, and it cannot be negative. So it has to be positive and cannot equal 1. So it's the same stipulations we had on the exponential functions. And this time, our value of x has to be greater than 0. Okay, so x can't be all real numbers this time. Logarithms are only defined for positive values on the inside. So this has to be positive. I can't take the log of 0 or log of -2. It's going to be undefined. Okay, so because they're inverses of the exponential functions, x and y get switched, like the domain and range get switched. So if you remember from the exponential functions, the domain was all real numbers. Well, now it's the range is all real numbers. On the exponential functions, the range was 0 to infinity. Now it's the domain is 0 non-inclusive, open bracket here, to infinity. Instead of having a y-intercept at 0, 1, we now have an x-intercept at 1, 0, swapping x and y. And instead of a horizontal asymptote at y equals 0, it's now a vertical asymptote at x equals 0. The y-axis is our vertical asymptote. Okay, so it's going to ask me to use my calculator to graph each of the following on the same coordinate grid. Okay, so let's try this out. Let's graph y equals log of x. And because they didn't specify a log here, it will default to base 10. So I'm just typing the word log. That's not great to do if you want to put in a different base. But you could also just use the log key over here, control, and then that button. But here's log of, x. Okay, and you can see it does default log base 10 of x. And here's my graph. I have a vertical asymptote on my y-axis, x equals 0, and an x-intercept at 1, 0. Just to prove to you, by the way, that it is the inverse, if I wrote that, the inverse of that, it would be y equals 10 to the x power. That would be the exponential. And if I graphed in the line y equals x, there you go. You can see those nice inverses reflect over that diagonal line, y equals x. Okay, but this is what our log functions look like. Rather than exponential growth, this guy's just shooting off to the right. Okay, so it asked me on the same grid to graph these other two, +2. And if you remember, this is basically in this form. So we'll write this down. Y equals a times log of x minus h plus k. So again, this is a logarithmic function, and those transformations like shifting left and right, up and down, being able to reflect over the x-axis when this is negative, or vertically stretch or compress it when I change its value, all of those things still hold true. So let's graph these other ones super fast. Y equals log of x plus 2. You might guess, because that's an h value, this is actually going to shift us left 2 units. And you can check that x-intercept has been moved left 1, 2 units. So my whole graph has been shifted left, including my vertical asymptote is now actually over at -2. Okay, there's the red equation. The last one it wants me to put on there is x plus 2 minus 1. And because this is a k value, as you've probably guessed, it's going to shift our graph up or down, in this case down 1 unit vertically. So now we've been shifted down 1. Okay, that doesn't change the vertical asymptote, but it does change those y values. Everything's been shifted down a little bit. Okay, so those transformations also apply to our graphs. Okay, last one. Just a reminder that the natural log function is a log with base e, that natural number, hence natural log. Okay. And that's generally written as ln of x. It's not in, I don't know, for some reason people think that's an I. It's just a lowercase l, ln of x. Natural log of x is log with base e. So those properties that we looked at earlier, somewhere back here, I don't know, this doesn't want to let me click. Somewhere back here, earlier, these properties still apply to the natural log. Just have to think of my base as being e specifically. Okay, so let's take a look at these. So if I have natural log of e to the 5th, it's going to help and I could say this equals x, it's going to help to rewrite this as log base e of e to the fifth equals x. And now I can see I have that matching base and what I'm taking the logarithm of. So going way back here, and the base and what I'm taking the logarithm of match, and there's an exponent, it evaluates to my exponent. So e log base e of e to the fifth ends up being x equals 5. And again, you could write this in exponential form, e to the x. If you wanted to do the extra work or rederive it, e to the x equals e to the fifth. And because my bases match, x has to equal 5. But that's the answer. You can use the property, you could rederive it if you have to, but there's our answer. Similarly, let's set this equal to x. This is in exponential form. So let's write it as a logarithm. Before I do that, actually, let's rewrite that as log base e. Ooh, I may not even have to do this. Log base e of 3 equals x. And wait a second, this does look like a familiar one that we saw earlier. E to the log base e of 3. E to the log base e of 3 should be 3. So my answer should be 3. If I forgot, we could actually change this to log form because it's currently in exponential form. And as a log, we would write this as log base e, because that's the base of my exponent, log base e of something equals something. And remember that it equals the logarithm. Log base e of 3 equals x. And because my one logarithm with the same base equals the other logarithm with the same base, the insides have to be equal. X has to equal 3. That's kind of the long way here. Really, if you remember that property, and remember that natural log is log base e, we can get straight to 3 much quicker. Okay, our last one here. Again, I'll just set this equal to x. This is log base e again, my natural log. And if I want to get this out of the denominator, we can use a negative exponent again. So I can write that as e to the negative second. And just like we did earlier, it actually matches the property we used up here. Remember when the base and what we're taking the logarithm of match, that our answer is our exponent. So I can go straight to my answer here, should be negative 2. Log base e of e to the negative second is negative 2. Or, again in exponential form, e to the x power equals what we're taking the log of, e to the negative second. And therefore, because those bases match, x has to equal negative 2. Again, if you know that property and memorize that property, you'll get there much quicker. Okay, it's a nice shortcut property, so you don't have to rederive it. Very last question. I know we're getting long here. Find the domain. So remember that all logarithms, including the natural log, are only defined for positive values inside. So there's a restriction on this expression. Anything inside of here, like x plus 3 this time, has to stay greater than 0. It cannot equal 0. It has to be positive. So to find my domain and calculate it from just the equation, I end up with that x has to be greater than 3. So there's my domain. If I wanted to write that out in that limit form or whatever other form's called, I don't know, my mind's spacing me now, we're going to say it starts from negative 3, non-inclusive, because it's not allowed to equal, so open bracket, to positive infinity. And there's my domain. Okay, so make sure you know these properties. We'll see those quite a bit. This one is like, it'll throw you off because we won't see it too often, but when it does, it'll throw you off. But knowing this property, b of b to the x equals x, that's basically the same as 2. And this other property will save you a whole bunch of time when we have to derive these logarithms. And definitely being able to switch from one form to the other is really important, like we did in that second page of examples. Okay, so your homework is written on the board. Good luck.